So problem 1833. In the book, I was not shown a diagram. It says to go to 1817, which you have to flip through the chapter to find. So this is the circuit that I had found. And then it gives you the value for the resistor, the capacitor, and the EMF. Okay, we're asked to find the time constant tau, find the time constant tau. And then find the charge on the capacitor after a period of 1 tau after the switch is closed. So for these RC circuits, when you're given an EMF, once the switch is closed, you're going to have a charging capacitor. And we have a formula for that. It's Q 1 minus E negative T over tau, which is RC. And then so it's interesting to note, before we move on here, that if you don't have a battery, and we're just something like that, and we close the switch, this capacitor is actually going to discharge. And we have a formula for that too, but that's not this problem. Okay, so first things first, we're asked to find tau, which we have a very handy formula in the summary of the chapter, which is the resistance times the capacitance. Now that gives us 75 kiloohms times 25 microfarads. And that gives us a value of 1.875 seconds. Okay, this is 10 to the 3 times 10 to the negative 6. And then we have 75 times 25, and that's what gives us this value. Because it would be, yeah, okay. Anyway, next, so that was part A. Next, for part B, we are asked to find the charge of the capacitor 1 time constant after the switch is closed. Now again, we can use this formula. And we're going to end up with, so we have Q, we need to find what Q is. That's one thing that we need to consider. Now 1 time constant after the, so what we're saying is that T, the T in this situation is going to be equal to tau. So that gives us tau over tau. So that's to the negative 1. All right. We also need to find this. Q is going to be, this is our maximum charge. And for this we have our EMF. Let's write the formula down. EMF times the capacitance, 12 volts times 25 microfarads. Okay, so then you just plug all that in. 25 microfarads times 12 volts times 1 minus e to the negative 1, and that gives you a value about 1.9 times 10 to the negative 4 coulombs. So that's how you do that problem. Let's do the next one right away. 18.35, I set this up so we're given another RC circuit. We have resistor, capacitor, an open switch. Right? Get rid of that. Okay, and then we have an EMF, right? We're given values for resistor, capacitor, and the EMF, and then we're asked to find the time constant once again. So the time constant, RC, is going to be equal to, what do we have, 1 mega ohm, 1 times 10 to the 6 times 5 times 10 to the negative 6 farads. And that's going to equal 5 seconds. Next, we're asked to find the maximum charge after the switch is closed. Well, the maximum charge, same thing as last time. It's going to be your EMF times your capacitance. Okay, so that's going to be, what was it? It was 30 volts times 5 microfarads, which is going to give you a value of, let's see, what do we do? 150 microcoulombs. Okay, easy enough. Then find the current in the resistor. Let me just double check that that's what they are. Find the current in the resistor 10 seconds after the switch is closed. Okay, now this one takes a little more work than the other ones, because before we were just plugging in a really simple formula and finding an answer, right? Now we have to actually think about how to find the current first. So remember that we have Q is equal to V times C. Oops, that's... What? There we go. Just trying to clean this up a little bit so I can write delta. Okay, and that is going to be equal to, when we have an EMF in the circuit, right? We also have that Q is equal to Q times 1 minus e to the negative t over tau. And then we can use these to solve for I, because we're going to have a time constant, right? We have a time constant, we're going to have a period, we can have a Q max, capacitance, so we should be able to solve for this no problem. So now what we're going to do is we're going to take this Q1, so I'm just setting, so I found these, right, by using the things that we know, and then I'm setting them equal to each other, and then I'm going to solve for I. So we have Q over C, 1 minus e negative t over tau, right, minus e, and then everything over R. And that's going to equal negative I. So then we take I is equal to, we're going to have E minus, now remember that Q max was the EMF times the capacitance, so that's going to be EMF times the capacitance, and now we have it over capacitance, right? This is, we'll call this epsilon C over C, and then 1 minus e negative t over tau, all over R. So if we're rewriting this, 1 second, need more space. There we go. So if we're rewriting this, then we have current is equal to epsilon over R, 1 minus 1 plus e negative t over tau. That's going to give you epsilon over R times e negative t over tau. That's your current. So all I did was I used this identity, right, for this RC circuit. We have the charge is equal to maximum charge times this term here. Okay. I also use the identity that the change in the potential times capacitance is equal to your charge. And we have this, the change in the potential is your EMF, the difference between the EMF and the internal resistance times current, times the capacitance, right? So plug this here, and then set them equal to each other, solve for I. That's what I did. Okay. So then we have values for all of this stuff. We have a 30 volt battery over a 1 mega ohm resistor times E this is, by the way, I'm plugging in everything. They gave us a value of after 10 seconds when the switch is closed. We have a 5-second time constant. plug all of this in, you're going to end up with 30 microamps e to the negative 2. Oops, these are seconds. These units cancel. I'm trying to get this to work. There we go. E to the negative 2, and plug all that in, and then you are left with a value of 4.06 microamps. That's the current in the resistor after 10 seconds from when the switch is closed.